Hi folks, we're starting a new unit. This is the last unit on computer simulation. I guess it's appropriate that it's the last unit because it's kind of what you do if you can't do any of the other things that we've talked about this semester. In other words, if you don't have a nice mathematical theory for modeling something, then you can always fall back on doing a computer simulation, or trying to do a computer simulation. Some systems are just a little too complicated to have a nice, neat mathematical theory. And so what you can do is you can try to simulate it on a computer, and then the plan would be to run your computer simulation preferably many, many times and see how it plays out on average, right? And do some statistics on what happens when you perform the simulation. Now, the same warnings about math modeling apply to computer simulations. That is, we don't try to model the real world exactly, and therefore we must choose which aspects of the real world are most important to us, and just try to get those crucial aspects, or at least some approximation of those crucial aspects that we're most interested in. There's actually many different types of computer simulation. I mean, you can do anything with a computer, basically, right? The particular type of simulation I'm going to be talking about in this unit will be what you might call a kind of a generalized Markov chain, in that it consists of states through which the system passes at one moment in time after another, right? So it's a sequence of states of the system over time. One important difference with computer simulations is that you're not limited to any finite number of states. In principle, you can have any number of states or even an infinite number of possible states. And on a computer, that wouldn't necessarily make the simulation any more difficult to run than would a system that has only finitely many states. And one thing that means is we can put any information we want into the states, right? So we can actually put whatever information would be convenient for us into the states. A simple example would be in some of those absorbing Markov chains where we wanted to determine how long it would take until the system reached an absorbing state. We did the calculation of the waiting times based on the properties of the N matrix, the fundamental matrix N. In a computer simulation, you could do it a little more directly. What you could do is you could actually include the time that's already elapsed in the state itself, right? You could simply record how many steps of the process have elapsed already. And then at the end of the process, you just record that number. You don't have to do any further calculations, right, in order to get the waiting time. Of course, on the downside is that, of course, that only gives you the waiting time for one particular run of the simulation, and we really want a theoretical average. So to make up for that, we have to run the simulation many times, maybe 1,000 or 10,000 times, in order to get some good statistics on what the average is likely to be. However, the computer does all the heavy lifting there, right? Once we've got the simulation set up, we can just let the computer run for an hour or whatever, however long it takes. And in the end, it's often easier to just do a computer simulation than to try to do the calculations, the matrix calculations or whatever. Okay, now you have to plan these things carefully. Okay, we're going to be writing basically computer programs to do this. And if any of you have had any experience writing computer programs, you know that planning and attention to detail is essential when you're writing a computer program. In particular, in our case, writing the computer program will be slightly simplified because I'll provide you with some Mathematica codes, a package that'll make writing simulations somewhat easier. So you don't have to do all the programming from scratch. However, you do have to basically design the system that we're going to be simulating from scratch. That is, you have to design what the states are and how one state changes into another state over time. And all that stuff you do have to work out in complete detail. And it's important to work out the ideas for doing that before you even touch the computer. So at the planning stage, don't even turn on the computer. Just think very, very carefully about, well, for one thing, what are the states of the system? Right? Are they, what is a state? What information determines a state? How do you tell one state from another? Right? What do you have to know about a state in order to tell one state from another? And, at a minimum, a state has to contain enough information to determine, or to allow you to determine what state will follow it in time. Right? So, in the case of like an observing Markov chain, take the case of the hunter who was hunting for, with either a bow or an arrow or a rifle, right? You have to know at each point in time which method he was using to hunt previously in order to determine what method he's going to use next time, right? That's a pretty simple case, right? In some cases, you might want to know something even about the recent history of the system. You might want to keep a record of what happened on the past couple of time steps, right? You might even want to have a little knowledge of the history. Technically, in a Markov chain, the probabilities of the succeeding state, the state that follows from the present state, depends only on what the present state is. But very often it's convenient to make the probabilities depend on some of the some more of the preceding states, maybe not just the previous one, but the previous 2 or 3 states. And that's somewhat easier to do if you're doing a computer simulation. You can incorporate that extra information about the history of the system into the current state itself. Right? But it's important when you're planning the simulation that you think about what kind of information has to go into defining what the state is. Right? Now, that information, it could be numbers, it could be strings, meaning letters or words, it could be logical symbols, it could true and false values, it could be lists of things, lists of numbers or lists of strings, or lists of logical symbols. It could be matrices. So basically any kind of data format that's appropriate for your system might be necessary, might be helpful in defining the state. All these different pieces of information I'll refer to as the internal variables of the state, or the attributes of the state. Right? So, for example, in the case of the hunter, one of the attributes of this state was the weapon she was using, right? Whether she was using a rifle or a bow and arrow, right? And maybe another attribute of the state would be whether she was successful, right, in bringing down a deer or not, right? So that's the very, very first thing to do, is to think very carefully about what information determines a state and how you're going to represent that information and what that information is going to look like, right? Is it going to be numbers or strings or letters? And list all the attributes of your state in as much detail as you can, so that you'll be able to write computer code to represent it when you have to. In fact, later on, when we actually, probably rather soon, when I ask you to submit a proposal for your project, the one thing I'll ask you to do in the proposal is to include as complete a description as you can of the attributes of your states. Right? So I'm going to want you to think about your system in enough detail in order to specify what the attributes of the states will have to be. Then, after being clear about what your states are and how you describe them and what attributes they have, the next thing to do is to think about how you would go from any particular state, at a current moment in time, to the state at the next moment in time. So I'll refer to that as a successor state. As a successor state, the state that succeeds the current state in time. And we have to have some way of calculating the successor state from the current state. And to be more explicit, what that means is we have to calculate all the attributes of the successor state. Right? That's what defines what a state is, knowing what the attributes are. We have to be able to calculate all the attributes of the successor state given the attributes of the current state. Right? Eventually, we're going to write mathematical functions to calculate all of these new values, the new values of the attributes for the successor state, starting with the values of the current state. But for the moment, when you're at the planning stage, just think about it in terms of mathematical functions. Use mathematical notation, and then also you can describe in words the series of steps you may have to go through. I don't know if you've encountered the word algorithm. An algorithm is simply a precise process for deriving a mathematical result, or really any kind of computing result, right? So an algorithm is just any kind of a step-by-step procedure for arriving at a result. So in addition to using mathematical functions, you can also use algorithms, right? So you can just describe very precisely, step-by-step, what you have to do to get from the current state to the next state, or even more specifically, how to get from the attributes of the current state to each attribute of the successor state. Okay, so now I'm going to talk about planning simulations in the case of a couple toy examples. These are examples that are relatively simple, and in fact, in all of these cases, we could actually answer the questions without doing a simulation, because the problems are simple enough that there exists a complete mathematical theory for solving these things. However, just to introduce the idea of simulation and to keep the extraneous complications to a minimum, I want to use these simple examples, right, to introduce the ideas. So the very first example is really simple. I bet you all know the answer to the question I'm going to ask here. Suppose you roll a fair die repeatedly until you get a 6. Right? So you just keep rolling a die until you get a 6. On average, how many times must you roll the die, right, before you get a 6? Or in order to get a 6, right? By the way, in the literature, there's some ambiguity about whether you count, whether the waiting time until you get a 6 just counts the number of failures you got before getting a 6, or whether it also includes the roll when you got a 6. And if you've had a course in probability, you may have heard of the negative binomial distribution. This is actually the number of failures you got until you got a certain roll. So for the record, I'm going to include the roll when you get the 6, right? So how many rolls it took to get the 6? Like I said, I think everybody probably knows the answer to this. If you've had a course in probability theory, this corresponds to the geometric distribution, and that's one of the standard distributions. So you probably remember this. You could probably, even if you haven't had a course in probability theory, you can probably guess the answer. But nevertheless, I'm just going to go through the whole process of simulating this on a computer, even though it's really not necessary, right? Because we can analyze this just by pure math. So how do we plan this simulation? Well, we have to have states that are basically going to correspond to the state of the system after each roll, right? After each roll of the die. And then we have to plan how to update the system when we roll the die the next time. And then we should also give some thought to what actually we're going to do when we run the simulation. Like how long will we run it? How do we know when to stop running it? That kind of thing. So okay, so here's the rolling a die example. The state attributes, I'll call them, there'll be a variable r, right? So a kind of a local variable for the state. R will be the value of the current roll. This will be a whole number 1 through 6, right? And it'll be, it's basically selected at random every time we roll. But the important thing at the moment is just that a state has an R value which represents the current roll. T will be the number of times the die has been rolled. So in other words, T is recording the time, how long this process has been going on so far. Then we have to have algorithms or procedures or functions for updating the state to the successor state, right, to the state at the new time step. By the way, I'll use the shorthand notation. I'll use R sub n for the new value of R and R sub O for the old value of R. In other words, the value from the previous time step, in this case from the previous roll, and Rn will be the value for the new roll. And similarly for all the variables, so in this case Tn will be the new value of time at the new time step, To is the value of time at the old time step. It does get a little confusing that these attributes, right, R and T, every state has an R and a T value, but in doing the update from one moment in time to the other, we have to distinguish between the old values and the new values. So this just seemed like a convenient notation to use, right, to distinguish between the old R and T values for the previous state and the new R and T values for the new state after the new roll. Okay, it's the update algorithms are pretty simple. The new roll we get simply by choosing a random number from 1 through 6 using a uniform distribution, right? We're assuming that this die is fair. The die that we're emulating, that we're simulating, is a fair die, so therefore we want to pick one of the numbers 1 through 6 using the uniform distribution so that they're all equally likely. The value for Tn, for the new value of T, is very simple. It's simply the old value of T plus 1, right? We've just incremented the time by 1, right? We're on to the next time step. Now, when we've got the simulation set up on the computer, what we're going to want to do is we're going to want to run it until a 6 is rolled. And we'll know that a 6 is rolled because the R value of the current state will be equal to 6, right? So we keep running the simulation until R equals 6, and then we can stop. And what we'll do is record the number of rolls. In other words, we'll record the time, right? So we could say that we keep running the simulation until R is 6, and then we record the value of T, right? What we'd like to do then is run the simulation like this a number of times, hundreds or thousands of times, and then we will collect the data from all of those runs of the simulation, and then we can calculate the average number of rolls that were required over all of these simulations. Right? So the second example is also about rolling a die. It's a little bit more complicated. This time I want to ask, on average, how many times must a fair die be rolled in order to get 3 6s in a row? Right? So now we're not just going for 1 6, but we want to get 3 consecutive 6s. Right? So this is going to take longer. It's just a slightly more complicated problem. Let me point out that both this problem and the previous one can be thought of, or could be formulated as absorbing Markov chains. That is, for example, in this case, you could think that you're rolling the die repeatedly. The absorbing state is when you've finally rolled 3 6s in a row, and then we can kind of stop the experiment, right? But we model that as an absorbing state. And then you would have states that represent various stages, states you could be in before you've achieved that goal. And you could set up the canonical matrix and find the the fundamental matrix and solve the problem that way. And you could do something similar for the previous problem, right? That's another way to analyze the previous problem would be as an absorbing Markov chain rather than just using the geometric distribution. geometric distribution is probably the simplest way to go. But nevertheless, despite its simplicity, I want to use this as an example for a computer simulation, precisely because it's so simple, right? It allows us to focus on the issues of the state attributes and the update algorithms and all that. Okay? So in this case, as in the previous case, the state attributes will include R for the current role, right? Number 1 through 6. It'll include T for the time, in other words, the number of roles that we've already performed. And in addition, in this case, we want to keep track of whether we've already gotten some 6s in a row so far, right? Maybe we're working on a partial streak of 6s. So if we've already got 2 6s in a row, then we only need one more 6 in order to achieve our goal, and then we can stop, right? So I'll use the variable L to represent the length of the current sequence of 6s. Of course, most of the time L is going to be 0, because most of the time we won't have rolled a 6 on the previous roll, and we won't have an existing run of 6s to be working on, right? So most of the time L will be 0, but occasionally we'll get lucky and we'll roll 1 or 2 6s in a row, and then L will be 1 or 2, and when finally L equals 3, then we know we can stop because we've gotten what we wanted. Now the update algorithms, again, are exactly the same for R and for T. The new value of R will be equal to a random number from the uniform distribution on the whole numbers 1 through 6. T and the new T is equal to the old T plus 1. L is a little more complicated. We could think of it as a piecewise function. Let me try that. Oh yeah, we could think of it as a piecewise function here, right? That we're saying that the new value of L is equal to either 0 if the current roll was not a 6, right? If we did not roll a 6, that means we don't have any streak of 6s. And in fact, if we had a streak going, we've just ruined it, right, by rolling a non-6. So we're back to 0, right? We're starting over. On the other hand, Ln will be equal to Lo plus 1, the old value of L plus 1, meaning we've extended our streak by 1 if the current value Rn, the value of the current roll, Rn, is actually equal to 6. So this means that we've actually rolled a 6 on the current roll, and then we increase the value of L by 1. Okay? So that is how we update the state, right? And the idea would be then, using these rules for updating, we run the system for maybe 1,000 times, right? We're going to want to run this 1,000 times. Each time we run it, we will run it until L equals 3. That's how we know we've achieved our goal, and that's how we know that we've gotten 3 6s in a row. And then when that happens, we can just record the value of T, right? And then we'll know how long it took on that particular simulation to roll 3 6s in a row. By repeating this 1,000 times, we'll have some statistical data that we can use to compute an average value to estimate the mean, right? And we should find, that this would agree with the result that we get from doing the absorbing Markov chain, right? By doing the analysis of the absorbing Markov chain, we would get an exact theoretical value for the average waiting time for this to happen. Of course, in doing a computer simulation, you will never get the exact theoretical value, but you should get pretty close to it, and you should get closer to it the more runs of the simulation that you do, right? The more statistics you gather, the more accurate your estimate of the theoretical average should be. The next example is from the Mackey and Thompson textbook, the Superfinite textbook. You imagine that a cat food company is running a promotion, and each bag of cat food that they sell contains a token with one of the letters C, A, T, or S, right? And if you collect a complete set of tokens that spell the word cats, then you win. Let's say a seal point, doll-faced, purebred Himalayan cat, right? That's the prize. Furthermore, let's suppose that the cat food company, as usual in these things, it plays a little trick on you, and not too bad, but 90% of the bags contain the letters C, T, and S in equal distribution, right? So in other words, 30% of the bags have C's, 30% have T's, 30% have S's, but only 10% of the bags have A, right? So this means you'll relatively quickly collect the C, the T, and the S, but it's harder to collect the A, right? So this seems to be a standard kind of marketing trick in these kinds of situations, right, when they're running this kind of promotion, that they make it easy for you, or relatively easy for you to collect some of the set, but then make one or two of the items difficult to collect, so you have to keep going back to the store and buying more in order to collect that final item that you need to complete the collection. So the question is, under these circumstances, how many bags on average must a customer buy in order to win the prize, right? To collect a complete set of letters. Okay. Now, in all of these cases of simulations, there's various ways to do this. I'm going to show you one way to do it, but there are others. So I'm going to say, well, first of all, let's just think for a moment. We want to represent the state after you've just bought a new bag of cat food, right? What kind of state are you in, right? So we probably want to describe what the current letter is that we just collected in the new bag of cat food. We also want to keep track of which letters we've collected up till this point in time, including all the earlier bags of cat food. And we also want to keep track of the time, because that, after all, is what we're interested in ultimately. How long is this going to take? So we have to keep track of all those things, right? So for the state attributes, I'll say we have a letter L that represents the current letter, right? The letter we got from the current bag of cat food. Now we also have, and of course time, as before, we'll have variable T will be time. Now, one way or another, we have to keep track of whether we've already collected each of the letters in either the current or in the previous bags of cat food, right? There are different ways you could do this. I'm going to do it using what are called Boolean variables, right? So I'm going to use this variable C. It's called a Boolean variable because its values are either true or false. Its values are not numeric values, they're logical values, right? So that's what a Boolean variable is. It's a variable that takes Boolean values, meaning logical values, true or false. So I'm going to say that C is a Boolean variable that's true if we've already collected the letter C, and it's false if we have not yet collected the letter C. And in a similar way, we can define Boolean variables A, T, and S, right, to keep track of whether we've already collected the letters A, T, or S. Okay, so we actually have a total of 6 state attributes, or 6 variables here. One of them takes a value as a string. It would be a letter, right, whatever the current letter is. 4 of them, the C, the A, the T, and the S, those are Boolean variables, and one of them is a ordinary numeric variable, the time, right, but only one of them. Okay, now, how do we update from one state to the next? Or in other words, how do we update the state after we buy a new bag of cat food, right? How do we update the system to reflect the new state? Well, L will be just a new random letter that we've chosen from the letters C, A, T, and S with the probabilities 0.3, 0.1, 0.3, 0.3. Respectively, right? So C is probability 0.3, A is probability 0.1, T is probability 0.3, and S is probability 0.3, right? So we'll just have to use some kind of a random process to select a letter at random with those probabilities, right? This will actually turn out to be easy to do on Mathematica. It has built-in functions that do things like this. So that's not going to be a concern. At the moment, all I want to do is I just want to be very clear about what the probabilities of each letter are, right? to make it easy for us later when we actually have to write the computer program, just lay out all the mathematical facts as clearly as possible here. Okay. A t, again, we update by just adding 1 to the old value of t to get the new value of t, right? We've bought 1 extra bag of cat food. Bags of cat food are how we measure time in this problem, so time has just increased by 1, okay? Now, how do we update these Boolean variables, right? So c is true or false depending on whether the letter c has been collected already or not. So the new value of c will be equal to, well, let's see. We could start off with the old value of c, c sub o, because if that's true, that means we've already collected c, the letter c in the past. And that means we don't have to worry about collecting it in the future, and therefore the new value of cn should still be true. We can represent this logically by saying that c0, or rather cn is equal to c0 or, oops, what have I done? C0 or, and then, in logic, oh, by the way, this symbol, this V symbol here, that's the logical symbol for OR, so it's used by logicians to represent the operation of logical OR, right? So this means Cn, the new value of C, will be true if C0 was true or something else, which I'm going to talk about, but this means it's guaranteed that Cn will be true if C0 was true, right? Because adding an OR condition cannot make something that was true false, right? Now, the second condition after the OR is that the new letter is equal to a C, right? So if the new letter ln is equal to a C, then that means that we've just collected a C, and that means even if the old value of the Boolean variable co, even if that old value was false, we still want the new value cn to be true because we just got that letter C, right? So this is a nice, simple, compressed way to represent this operation. We say that the new value of Cn is equal to the old value C0, or that the new value was equal to, the new letter was equal to C. Right? If either one of these things are true, if either the old value of C0 was true, or if the new letter is equal to C, if either of those things is true, then we can regard the letter C as having been collected, and therefore the new value of the Boolean variable C will be true. And in a similar way, we update the Boolean variables A, T, and S. Right? They are all updated in exactly the same way. The new value of A will be true if either the old value was true or if the new letter is an A. Right? And same for T and S. Okay? So if we can manage to represent this algorithm in the computer, right, or in any kind of computing device, then what we'll do is we'll just run the whole system until all four Boolean variables, C, A, T, and S, until all four of them are true. And by the way, this wedge symbol, it's like an upside down V, that's the logical symbol for the logical operation AND, right? So this says that C and A and T and S, right, that all four Boolean variables are true, and that means that we've collected all four letters. So we will run our simulation until this happens, until all four Boolean variables are true, and then we can stop the simulation and record the time. Right? That'll tell us how long it took to collect all four letters. I said earlier that this method of simulating systems is kind of a generalization of Markov chains, right? And one consequence of that is that it's very easy in this with this Mathematica package we'll be using, and with this approach, it's very easy to to model standard Markov chains on a computer. Again, in a sense, there's no reason to ever do that, because if you have a standard Markov chain, you can analyze it using the mathematical theory of Markov chains. Although there might be situations where you have such a big matrix that actually doing all the computations might be impractical, even on a large computer. You might have 1,000 states, and then the transition matrix would be 1,000 by 1,000. That would have 1,000,000 values in it. It might actually not be so easy to compute it, and it might, even, in a case like that, actually be easier to do a simulation on a computer rather than trying to compute the exact values. In any case, it is easy to model just a standard Markov chain on a computer. In fact, we already did cases earlier. Some of the first two toy examples we did could have been thought of as absorbing Markov chains, right? And we can do them on the computer easily. Here I'm going to do a question regarding a regular Markov chain, where we're looking for the long-term probabilities of being in each one of the states, right? So suppose we have a standard Markov chain. Even assume it's a regular Markov chain, right? So that it's ergodic and period 1, and so it's guaranteed to have a nice, well-defined, long-term stable vector. And suppose we'd like to try to calculate that stable vector kind of experimentally, or in other words, using a computer simulation, right? Well, we use the computer simulation to estimate the long-term stable vector rather than computing it exactly using the mathematical theory, right? So suppose we have a system that has n states, and therefore it has an n by n transition matrix, P. And the question, of course, is in the long run, if we run the system forever, what fraction of the time in the long run does the system spend in each one of the n possible states? The state attributes, the things we have to keep track of in the course of running the simulation, are what the current state is. So I'll call that little s, right? That'll be one of the local variables in the state, whatever the current state of the Markov chain is. Well, also, by the way, this might be a little confusing. We have to distinguish here between the states that we're using for our simulation and the states of the original Markov chain. In the original Markov chain, there were only n states, but in the simulation, the states are more complicated. The simulation states are going to include the state of the original Markov chain, which will be 1 through n, but they're also going to include the time, right, the number of time steps that have already elapsed in this system, and one other thing it'll include will be a vector, that is a list, of the number of times each one of the states of the original Markov chain have occurred. Right? So boldface C, that's going to represent a vector of numbers representing how many times each one of the n states has occurred so far up through time t. Right? So that's something obviously that we'd like to know in order to answer this question. If we know how many times the Markov chain system has been in each one of the n states, then we can calculate what fraction of the time it's been in each one of the n states, and then we can estimate what the stable vector will be based on that. Okay, so in this case we've got the states for the simulation actually contain three variables. S is a number, T is a number, and C, which is a vector, right? Whereas the states in the original Markov chain were really just a single number, really just the number 1 through n, right? It could be in any one of the n states. Notice that means the states in the simulation, theoretically there's an infinite number of possible states in the simulation, right? Because T and C could have numbers that are basically unbounded. S has to be a number 1 through n, so there's only finite many possibilities for S. But for T and C, there are actually infinitely many values they could take. So in our computer simulation, the states run over an infinite number of possibilities. Okay. even though we're only simulating a Markov chain that had only n states originally. Right? Okay, the update algorithm. Well, let's see. Of course, Tn will be equal to To plus 1, right? We'll just increment the time by 1. That's simple. Now, how do you go from a particular state in a Markov chain to a state at the next time step in the Markov chain? Well, that's what the transition matrix P tells you, right? That gives you the transition probabilities for going from one state to another. In particular, the entries in the in one particular row of P, like for example the ith row of P, they tell you the transition probabilities assuming that you were previously in state I, right? So the entries in the second row of P tell you the transition probabilities assuming you were previously in state 2 of the Markov chain, right? So what we'll do is, in order to generate a new value for Sn, right, the new value of S, a new state, we will look at what the old state was, S sub O, and we will look at the row of P corresponding to S sub O, right? We'll look at that row of P, and we will use those probabilities in that row of P in order to pick a random new state, right? In order to pick a random value for Sn, which will be the new state of the Markov chain. Again, it turns out that there's some nice built-in functions in Mathematica. We can do this very easily. At this stage, the important thing is just to be clear about where the probabilities come from. So it's important just to be clear that the probabilities for determining what Sn will be come from the row of P corresponding to the previous state, S sub O. Okay? So that's the important thing to be clear about here. And we can worry about how we actually code it later. How do we update the C vector? The C vector, which is a list of the numbers of times each state has occurred. Well, basically, the new value of C is going to be almost identical to the old value of C, right? Except that one number will be incremented by 1, right? Whichever state has just occurred, whatever the new state is, we'll have to increment the corresponding entry in C by 1, right? So I'm just writing out in words here the procedure that will follow. We're saying that the new vector Cn will be exactly the same as the old vector Co, except that we'll add a 1 into the component corresponding to whatever the current state is, right? Because we've just reached that state one extra time, so we have to increment that count by 1. Okay? Notice in this situation that it's rather important that we update the value of S before updating the value of C, right? We have to know what the new value of S is, what Sn is, before we can update the value of C. We can find out what Cn is, right? So that is typical in more complicated, any reasonably complicated computer simulation. You will have to update the attributes of the states in a particular order. You can't just update them at random. You usually have to do it in a particular logical order. Now, you don't have to worry about this too much because the computer will actually determine what the logical order is for updating the states. However, you do have to be aware of a situation in which one state depends on another and vice versa. So for example, suppose that in order to update Cn, I need to know Sn, which is the case here, right? In order to update Cn, I need to already know what Sn is, but suppose that in addition, I described an algorithm for updating Sn that required knowledge of what Cn was. Well, that would be a problem. That would be circular, right? Because Cn would depend on Sn and Sn would depend on Cn, and there'd be no way to actually get started in that situation. So that's one thing to be alert to, is if there seemed to be some kind of a circular dependency among your attributes when you're updating them, right? It should be possible to update them in a specific order without ever encountering any circularities like that. Okay? So just be aware of that. If you're running into a kind of a circularity, then you're doing something wrong. Then you should go back and redefine your states, probably, so that you can update them in a particular order without encountering any of those circularities like that. Now, once we get the state set up and the update algorithm set up, then the idea would be to run the simulation for a large number of times. Let me be careful. We'll run a single simulation for a large number of time steps, right? For example, we'll run it for like 1,000 time steps, 1,000 transitions of the Markov chain. Now, doing it for 1,000 time steps, that's still only one run of the simulation. That's just a single run of the simulation. But we've run it for 1,000 time steps, so at that point, we've got a pretty good indication of how much time the system is going to spend in each state in the long run, right? 1,000 time steps, that's close enough to the long run that we can make an estimate now of the stable vector, right? And because the stable vector represents the long-term probabilities of being each one of the states. So at that point, after we've run the system for 1,000 time steps, then we look at the vector c, which counts up how many times the system has been in each one of the possible states, and we divide by the time, right? We'll divide by 1 over t, and that'll give us basically the frequency with which the Markov chain is in each one of the time steps, right? This will give you a probability vector, right? Each one of the entries in this will now be a probability, and they all add up to 1. And it'll tell us what fraction of the time the system spent in each one of the states in this particular run of the computer simulation, okay? Again, that's only one run of the simulation, so what we should now do is repeat this run hundreds or even thousands of times in order to see what this average turns out to be over many, many repetitions of the run, right? So once we've collected data over several hundred or even 1,000 runs of the simulation, then we can take the mean of these averages to get a better overall average of what the fraction of time spent in each one of the states is likely to be, right? So doing that should give us a pretty good estimate for the stable vector w, and in fact that's something we should do. We should probably compute the exact value of w using the Markov chain theory, and then also do it on the computer simulation to make sure the computer simulation is working correctly. If the computer simulation is working correctly, our estimate for the average time spent in each state should be pretty close to the theoretical values, right? Okay.